All right, we're going to look at optimization now. So we use this to, if we want to maximize or minimize different quantities, we want to know like, oh, what's the least amount of time it's going to take for this, or what's the greatest amount of profit we could get. Or, maybe we're making shipping boxes and we want to minimize the cost of materials. So like, what's the maximum volume we could have with the minimum amount of spending. And yeah, so here's some problem solving techniques for these kinds of problems. So obviously you want to read the problem, circle, highlight, underline any key information. It's just good word problem solving strategies to begin with. Maybe we want to draw a picture, label any constraints or variables for unknowns. You don't necessarily always have to draw a picture, but sometimes it's helpful. And we want to write a primary equation. So something we can use. Sometimes it might be obvious, sometimes it might not be obvious. But we want a formula for the quantity that's going to be optimized. So if we want to, have the maximum volume of this box, then we're going to need the formula for the volume of a box, right? And then we're going to have to identify any constraints or limiting factors. And we might have to write a secondary equation that has more information for us to be able to optimize what we need. So there might be multiple variables involved. So we might have to solve one equation for a variable so that we can substitute it into the original so that we're in a nice, one variable equation so that we can solve. And then we might have to figure out our domain. Sometimes you can do that before. Sometimes you can do it after. And then figure out what our extrema are. If we want to maximize or minimize, we want to find a derivative set it equal to 0 and find, is that a maximum or a minimum, and what did we need, right? And then we'll just answer the final question. All right. So let's look at a pretty basic one here. So I want two positive numbers such that the sum of the first and twice the second is 64, whose product is a maximum. All right, so we want to maximize a product. So that's area. It's two numbers, right? I don't know what they are, so let's just use X and Y. So area, or product, I guess I should say, would be X times Y. Well, that's three variables. In an equation, I need only two. So let's see if we can make another equation. So the sum of the first number and twice the second. So I don't know what the numbers are. So how about the first number's X and the second number's Y? So the sum of the first and twice the second is 64. All right, I think I can solve that one. The X plus 2Y equals 64. I think I can solve that for X or Y and use the area one and find that maximum. I think it'd be easier to isolate X. X, I can take 64 and minus 2Y. And let's substitute that in. So instead of X, I have 64 minus 2Y and then times Y. Let's go ahead and just distribute that. So 64Y minus 2Y squared. And we should be able to recognize that that's a downward facing parabola, right? So we're going to have a maximum. And I just need to find it. So I want to find the two numbers. So to find the maximum, you could analyze the quadratic using your pre-calc knowledge, or we can do our calculus and do our derivative. So 64 minus 4y, right? And then we want to solve for 0. You can add 4y to both sides and then divide by 4. So y is 16. Write that over here, 16. And then I can find the other one. It's 64 minus 2y. So 64 minus 2 times 16. So 64 minus 32, which is 32. And there's the two numbers, 32 and 16. All right, we want to construct a box whose base length is 3 times the base width. The material used to build the top and bottom costs $10 per square foot. And the material used to build the sides costs $6 per square foot. If the box must have a volume of 50 cubic feet, determine the dimensions that will minimize the cost of building the box. Right? All right, this one I might want to draw a picture. So I have a box whose base length is 3 times the base width. So we got width and then 3 times that. And that's the bottom. I don't know how to draw this box. Okay, now I've drawn a box. Let's do 3W and W. All right, so we know that, I don't know the height. Let's just call that H. Okay. Let's figure out some other things we need. So we want to minimize the cost. Let's figure out our cost equation. So we have the material to do the top and the bottom. So 3W times W, so 3W squared. And then that's $10, so times $10 plus the sides. All the sides cost 6. All right, so 2 of the sides are 3WH, right? And then the other 2 sides are WH. But there's 2 of these. I forgot about that. All right. So then clean it up just a little bit. So it's going to be 60W squared plus 36WH plus 12WH. So really 60W squared plus 48WH. Right? And then I probably want some function for H. So I know the volume is 50 cubic feet. And volume is length times width times height. So 3W times height. So the height, if I just divide, is 50 over 3W squared. So now my cost is going to be 60W squared plus 48W times 50 over 3W squared. I can probably clean that up a little further. Let's see. 48 divided by 3 is 16. What's 16 times 50? 16 times 5 is 80. So add a 0, so 800. And then W over W squared is over W. All right, so this is our cost function. And we want to find the minimum. So I need to find a critical value, right? And let's see. So the derivative, we get 120W. And then really that's 800 times W to the negative 1. So it's going to be minus 800. And then W to the negative 2. Which I'm going to rewrite as W squared in the denominator. To find the critical value, we want to have it equal to 0. Then I want to add that 800 over w squared. And then maybe do some cross multiplying here. And then dividing. Let's see, what's 800 divided by 120? Let it be a nice number. And it's not. Okay. As a fraction, let's see, 800 divided by 120. They both have zeros. They're both at least divisible by 4. So that's 23. So 20 thirds. But then I want the cubed root of that. Oh my goodness. So 20 thirds. And then cube root. I get about 1.88-ish. All right. So then we could use two things. We could say, hey, let's use that first derivative test and say, hey, 1.88, let's check values on either side. And let's see, let's do 1. And how about 2? So if I plug in 1 into my derivative, I get 120 minus 800, which is a negative number. And if I plug in 2, let's see what that gives me. That's 240, and then 800. See if I plug in 2, that'd be divided by 4. So I get a positive. And then that creates that minimum value there. So, okay, we are good there. So we have a width of 1.88. We have a length, which is 3 times that, 3 times W. So 3 times 1.88. See what that is. 3 times 1.88 gives me 5.64. And then the height was 50 over 3W squared. So 50 over 3 and then 1.88 squared. So 50 divided by 3 times 1.88 squared gives me 4.7, wow, round it, 72, 4.72. And there are the dimensions. Did it ask for the volume? Oh, we already had it. Never mind. Okay. Let's do another one. Rancher plans to fence a rectangular pasture adjacent to a river. Pasture must contain 180 square meters in order to provide enough grass for the herd. So that's an area. So area is 180,000. What are the dimensions that require the least amount of fencing if no fencing is needed along the river? All right, so how about let's make this X, Y, and X because it's rectangular. And we need perimeter. So perimeter is going to be 2x plus y. And then area is x times y. I want to least amount of fencing, so I want to minimize the perimeter. So area is 180,000. And why not solve for y? So y is going to be 180,000 over x. So perimeter is 2x plus 180,000 over x. Let's do a derivative. So 2, and then minus 180,000. That'll be x to the negative 2, which is just x squared in the denominator. And I want to find some critical values. So I can set it equal to 0. And then I'll add the 180,000 over x squared to both sides. And then multiply both sides by x squared. Divide by 2. And then take the square root. The square root of 90,000. Ooh, it's 300. Obviously, I would get a plus and minus when I'm taking the square root, but domain-wise, we're not going to have a negative length of fence. So 300. I can double check that 300 is a, let's see, we want to minimize it. So I'm thinking we want that to be looking like this. So let's double check. So how about let's plug in 1. And if I plug in 1, 2 minus 180,000 is definitely negative. So it is for sure that decreasing there. And then something bigger than 300, I don't know, 400. So let's see, 180,000 divided by 400 squared is actually 1.125, and 2 minus 1.125 is positive. So we are good here. So this does create a minimum. So one dimension is 300. So x is 300. And y is 180,000 divided by x. And 180,000 divided by 300 is 600. All right, so there we have our dimensions. All right, let's try another one here. So an open box is being constructed from a piece of sheet metal, 18 inches by 30 inches. And we're going to cut out squares of equal size from each corner, and then we're going to bend the sides up. What size squares should be cut to make a maximum volume, and what is the maximum volume? All right, so we have a rectangle that is 18 by 30, but then we're going to cut squares out of each corner to then fold up. And I don't know what the side lengths are, right, that I'm cutting out, but they're squares. So my new length, I have 30, and I'm cutting an x here, and I'm cutting an x here, so minus 2x. And then for that same reason, I have 18, and I'm cutting an x, and cutting an x, so minus 2x. All right. So the volume is what I want to maximize. Length times width times height. So volume, length, 18 minus 2x, width, 30 minus 2x, and then the height is just x, because I'm going to just fold up these corners here, right? When I fold it up, they have a length of x. And I think we can go from there. So let's see. I'm going to distribute everything out. So let's see here. 18 times 30 is 540. And then I'm going to distribute the x as I go. And then I have 18 times negative 2, so negative 36x, but I have to distribute that extra x. And then minus 60 x squared plus 4x cubed. Then I'll combine some like terms. So 96x squared. Now I can do a derivative. So 540 minus, let's see, 96 times 2 is 192, and then 12x squared. Now I want to find the zeros, and I'm hoping all these numbers are divisible by 12 so I can factor. So let's see, 540 divided by 12 works. I'm writing this like I know it's going to work. Let's see, 192 divided, oh, it does. Works. So I have factored out a 12. And then let's see. Do I know two numbers that multiply to 45 and add to 16? So multiplies to 45 but adds to negative 16. So they would both have to be negative. So let's see. 1 and 45, 3 and 15, 5 and 9, 6, 7, 8, 9. I don't see any that work. Okay, so factoring is not going to work. But we have a nice handy dandy quadratic formula, right? Negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b plus or minus b squared minus 4ac all over 2a. Let's see what that gives. 256 minus 4 times 45 leaves me with 76. 76. You know what? Let's just get the two numbers. So 16 plus the square root of 76 divided by 2. So 12.36. And then we got to do the minus. So 16 minus the square root of 76 divided by 2. And here's one where we're going to check the domain here. Because if I do 12.36 times 2 and do 18 minus that, I'm going to get a negative number. So not in our domain, right? So I'm going to have to go with 3.64. I can round that to 4. 18 minus 8 works. 30 minus 8 also works. So x needs to be 3.64 inches. And then we want, what is the volume? And volume is back to this one here. So volume is 18 minus 2 times 3.64 times 30 minus 2 times 3.64 and then times 3.64. Let's see. I think I can do that all in the calculator. So 18 minus 2 times 3.64 times 30 minus 2 times 2.3. Oh my gosh. 30 minus 2 times 3.64 and then times 3.64. So I get 886.55 and then be cubic inches. Right? What are the dimensions of an aluminum can that can hold 40 cubic inches of soda and that uses the least amount of aluminum? Assume it's cylindrical. Gosh, that was terrible. And my circles aren't the same. And capped on both ends. So we know the volume is 40. Now we need a volume formula. Pi r squared height. All right, so 40 is pi r squared height. And then aluminum. So we want the surface area. So surface area. We have two circles. So 2. And then what is the area of the circle? Pi r squared. And then if we were to cut this out and like make our shape. Oh my gosh, that was awful. I just can't draw. We'd have two circles and a rectangle. I can't. So the rectangle is going to be the height. And then the length of this rectangle is actually the circumference of the circle. So 2 pi r. All right. So let's probably solve this equation for h. I think that'll be a little easier than to have square roots everywhere. So the height is going to be 40 over pi r squared. So that my surface area is going to be 2 pi r squared plus 2 pi r times the height, which is now 40 over pi r squared. Let's clean it up. So 2 pi r squared is going to be 80. The pi's will cancel and one factor of r will cancel. Now I can do derivative. So that's going to be 4 pi r minus 80 over r squared. Set it equal to 0 to find those critical numbers. Let's add 80 over r squared. And then multiply. And then divide. Which, let's see. We'll take the cube root. So 80 divided by 4 pi. And then the cubed root of that. I get 1.85 for the radius. And then what all did we want? The dimensions. All right, so we have a radius of 1.85. And then we need a height. So the height is that 40 over pi r squared. So 40 over pi and 1.85 squared. Let's see what that is. 40 divided by pi times 1.85 squared. Going to give me about 3.72. So that's my height. Alrighty. Which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? If I just look visually what this looks like, downward facing parabola that's shifted up 4. It's going to look, let's see, our zeros are going to be at 2 and 2. And we want what points on the graph are closest to 0, 2. Okay, so we want to minimize a distance. Woo. Alrighty. So let's recall the distance formula, right? So distance formula is the square root of change in x squared plus a change in y squared, right? So we can plug in some numbers, right? So let's see, our change in x. We want the difference in the x values. So I don't know what one of the x values is, but I know the other one is 0. So x minus 0 squared. And then the change in y's. So, okay, I don't know the y value, so 4 minus x squared. And I do know the other y value, that's 2. Let's clean this up. So x minus 0 squared is x squared. And then 4 minus 2 is 2. So 2 minus x squared squared. I think I can even go further with that. So we'd have 2, oh my gosh, minus x squared squared. So let's see, 2 times 2 is 4. And then I'd have negative 2, negative 2. So negative 4x squared. And then a positive x to the 4th. And then let's go even further. And let's put in standard form. So x to the 4th minus 3x squared plus 4. I don't want to minimize this. And I'm going to do something a little sneaky here. So, would you agree that if I just take the minimum of this, would you agree that if I took the square root of that quantity, it would still be a minimum. I same can go for maximum, but would you agree? If I find that 40 is the minimum value of that polynomial, wouldn't it also be true that the square root of 40 would still be the minimum? So how about instead of doing chain rule and everything, I can just find the derivative of the inside. So 4x cubed minus 6x. And I want to solve for the zeros there. Take a GCF of 2x out. Be left with 2x squared minus 3. So one of them is 0, which should make sense. Because the closest point, if it was the point, it would be the minimum distance. And then I would add 3, divide by 2, and take the square root of plus and minus the square root of 3 over 2. All right. I can check the values, right? I can do negative square root of 3 over 2, 0, and positive 3 over 2. And I can check some values here. So what is the square root of 1.5? That's 1.2247. So I could try -2, I could try -1, +1, and +2. All right, so I'm going to go back in. I'm going to plug my function in so I can just type in some values here. So my function is x to the 4th minus 3x squared plus 4. And I'm just substituting in those values. So if I do -2, I get +8. If I do -1, I get positive as well. Now if I do +1, I get 2. And then, I don't have any sign changes here. So did I? Oh, because I plugged that into the original like a silly freaking goose. I need to plug into the derivative. Silly me. All right, so 4x cubed minus 6x. Try that again. So -2 gives me a negative number. -1 gives me a positive number. So we are switching from negative to positive. So we do have a minimum there. So that's going to be a value. And let's do +1 gives me negative. But that's going from increasing to decreasing. So that's creating a maximum. So I don't want that. And then let's look at 2. That gives me positive. So that's another one. So positive root 3 over 2. And then I can get the actual y values by substituting them back into the original. Y equals 4 minus x squared, right? So 4 minus 1.5 is what, let's see, 2.5? And then it would be the same over here because the squared is going to cancel out that negative. And there we have it, some points that are minimum distance away from the point 0, 2. All right, so I have been doing the first derivative test and looking at, all right, does it make a maximum or a minimum? There's some other methods for justifying the way that things are. We can use the extreme value theorem if we're given endpoints. We need to have endpoints and we need to know that the function's continuous. Been doing the first derivative test, right? Or we could do the second derivative test, and if we plug it into the second derivative, if we get a negative, it's concave down. It's positive, it's concave up. So it'll tell us if we have a maximum or a minimum. All right. So just some different methods on justifying. I've just always used that first derivative test. And I think this is the last problem here. All right. So we have a boathouse for a sports club. It's situated along a straight shoreline. You row your kayak out 2 miles from the nearest point on the shoreline and then paddle back to shore at an angle. You want to reach sports club, which is 6 miles down the beach. You're training for an event that includes rowing and running. If you can row at a rate of 3 miles per hour and jog at a rate of 5 miles per hour, what's the least amount of time required to reach the sports clubhouse? And then how far is that clubhouse? How far from the clubhouse should you beach your kayak? All right. Kind of try and draw a picture here. Okay. So this is you out on your kayak. We are 2 miles for the nearest point on the shoreline. But we're going to row back at an angle. All right, and we'll beach here. And then we'll get to where this clubhouse thing is. So let's see what else I know. That was 2 miles. You want to reach the sports club, which is 6 miles down the beach. So this entire thing is 6 miles. And then we want to beach the kayak and then walk the rest of the way. So I don't know this distance here, but I know that this would be 6 minus x. All right, what else do we know? I know my rowing rate. I can row at 3 miles per hour and jog at 5 miles per hour. Okay, so I want to, what else do I know? I know that distance is a rate times time. And I know I want to minimize my time. And my time is made up of rowing and jogging, right? All right, so see what else I can piece together here. So, do we see what I see? Little right triangle here. Because isn't this distance here how much we would have to row? So couldn't we say that, hey, rowing distance is x squared plus 2 squared equals row squared? So really x squared plus 4, and then I would square root it, right? That's my distance. And then, let's see, jogging is the rest of the way here. So that's 6 minus x. If I rearrange the distance, here, let me write this. Jog distance is that 6 minus x. Distance is rate times time. Well, I want time. So time is distance over rate. So for rowing, right, my distance is that square root of x squared plus 4 over my rate, which was 3. And then jogging, the distance was 6 minus x over my rate, which was 5. Right? So now I want to minimize that. So let's take a derivative. I'm going to do a couple things here. I'm going to make that a 1/3 multiplier and then do the derivative of this, which is going to be 1/2 x squared plus 4 to the negative 1/2 times 2x. And then 6/5 is a constant, and negative 1/5 x, the derivative, is just negative 1/5. Okie dokie. So these 2's will cancel out. I'm going to clean this up. I know I'm going to set it equal to 0. So I'm going to be left with, let's see, 1/3. Let's just go ahead and drop that down to the denominator. Let's add 1/5 over. Then maybe cross multiply. Maybe divide by 3. Square both sides. Subtract 4. I'm running out of room here. Let's see if I subtract 4. It's really subtracting 36 over 9. Right? So if I square both of those. Oh, I see where my mistake is. I forgot my x up here. That should be an x, that should be an x, which means that should be an x. Which means I have messed up here. This should be an x, and this should be an x squared. So let's back up a little bit to that step. Square both sides, so I get x squared plus 4 equals 25/9 x squared. And then we can combine some like terms. So then I'll subtract 1. So subtract 9 here. Sorry, 9 over 9. So I get 4 equals, and 25 minus 9 is 16, right? X squared. And then divide both sides by 16. Gosh, I'm just making mistakes all over the place. I'm forgetting my over 9. Oh my lord. 16 over 9 x squared. And then multiply both sides by 9 over 16 so that I get x squared. And then that would be 9/4. Then take the square root and I get positive and negative 3 over 2. We wouldn't use the negative time, right? So we'd use the positive, or sorry, negative distance. X is a distance here. And now we can figure out what else we need. What's the least amount of time required to reach? So now let's plug in the 3.2. So our time was this formula here. And now I want to plug in the 1.5. Let's figure out what that is. 1.5 times 1.5. And then add 4 and square root that and divide by 3. And then add in 6 minus 1.5 divided by 5. And I get about 1.73. The time or the rates were in miles per hour. So 1.73 hours. That's how long it'll take. And I think it asked something else. How far should you beach the kayak? So that's 6 minus the 1.5. So that's going to be 4.5. And there we have it. Sorry, with all my little mistakes there, it took a little while. But there's optimization for you. So, if you have any questions, let me know.